So we're about to go into section 5.2 and 3, where we talk about passive transport and active transport. And so I wanted to make sure we had gone through this table because the table is a summary of both of those sections. So if you think about it, cells, every one of the cells in our bodies and in the cells that make up other organisms have to take in important molecules like oxygen, gas, and water, of course, and sugars, amino acids, for the nutrients, and then sometimes large molecules called macromolecules. And then there's waste that the cell builds up that it needs to release. And so anytime these molecules enter the cell through the phospholipid bilayer, and a good example of that would be oxygen and carbon dioxide gas. They're very small molecules and they're lipid soluble, so they can just scoot through the phospholipids. And they always move from where their concentration is high to where their concentration is low. So we call this diffusion. It's a passive process. And it says here the requirement is a concentration gradient, and that just means a concentration difference. That means outside the cell, the concentration has to be different than it is inside the cell. So going back to our example one more time. So here's a carrier protein, and you've got these green molecules. We'll just say that this is oxygen gas needing to come into the cell. So, I'm sorry, it can't be oxygen, can it? Because it wouldn't come through a carrier protein. Let's say that it is glucose. Glucose is moving into the cell from where its concentration is high outside the cell to where the concentration is low inside the cell. That's a concentration gradient. It's a difference in concentration on one side of the membrane and the other side of the membrane. So diffusion only requires a concentration gradient, and it only requires that the molecules move through the phospholipids. It doesn't require a carrier or a channel protein. Facilitated transport is identical to diffusion, but the molecules tend to be polar or have a charge, like sugars and amino acids, rather than oxygen and carbon dioxide gas, which are lipid soluble. The molecules are water soluble, okay? And a concentration gradient is required, but the molecules still move from their high concentration toward their lower concentration. And they also have to move through a channel or carrier protein. So both of these first two processes, diffusion and facilitated transport, are passive. They don't require energy. Active transport is just like facilitated transport, but it does require energy. A carrier protein plus energy. Transports the same type of molecules, but this time instead of moving toward their lower concentration, they're moving toward their higher concentration. It's kind of like this. Your cells need all the glucose that they can get and all the amino acids that they can get. They need to pull in nutrients even when their concentration is higher inside the cell. They still need to keep pulling those nutrients in because our cells need those nutrients. So they'll use active transport to continue to move those nutrients like sugars and amino acids, and sometimes even charged particles like ions, like sodium and potassium and magnesium. Active transport will be used to move those molecules in, even though their concentration is already high inside. And then bulk transport also requires energy. So active transport and bulk transport are both active transport processes, but bulk transport uses vesicles. It has nothing to do with a concentration gradient. It's just moving macromolecules or a bulk or large amount of material into or out of the cell. So let's move on to section 5.2 and make sure we get the terminology. A review: if it is a solution, then the two parts are the solvent or the liquid portion and the solute or the dissolved solid. Diffusion is the movement of molecules down or with their concentration gradient. That means toward their low concentration. And there are certain factors that affect how fast diffusion occurs or the rate of diffusion. Temperature, for example, warm temperature will cause diffusion to occur at a faster rate. Higher pressure will cause diffusion to occur at a higher rate. Electricity will cause diffusion to speed up. And molecular size, so the smaller the molecules, the faster that they will diffuse. Large molecules diffuse slower. We always see these images of dye being dissolved in a beaker of water or a container of water, but I don't even like that example because there's no plasma membrane, and every type of transport that we're going through, that we're talking about, is across the plasma membrane. So let's look at this example where in deep in our lungs, we have air sacs called alveoli. They literally are composed of, their lining is a single layer of very, very thin cells. And so we have the plasma membrane of those cells, that is, and the plasma membrane of the blood capillaries that are attached to the alveoli. Those plasma membranes are the only barrier between the oxygen leaving the lungs and entering the blood. You have these thin plasma membranes from the cells that line the lungs and the cells that line the capillaries. So oxygen literally diffuses from its high concentration in the air sacs of the lungs to its low concentration in the blood. And it literally diffuses through those phospholipids from high to low concentration down its concentration gradient. And carbon dioxide does the opposite. Carbon dioxide would be low in the alveoli and high in the blood. So carbon dioxide would diffuse into the alveoli, whereas oxygen diffuses into the blood. But both of those gases are lipid soluble, and they're diffusing through the phospholipids. Then we have osmosis, which is the diffusion of water. So osmosis is the diffusion of water across the plasma membrane. And basically what happens there is that water, a lot of times water is more easily able to move across the plasma membrane than the solutes are. So water will move toward the solute. When I teach anatomy and physiology, a lot of times I always tell my students water follows salt. Water follows the higher sodium concentration, but sodium is not the only solute. So water is going to follow high solute concentration. It's going to move toward the higher solute concentration. And the more a difference in concentration there is, the more osmotic pressure there's going to be. And that's the pressure that tends to draw water toward the higher solute concentration. So if you look at an example like this, so what we have on slide 27 in figure 5.7 is something called a Thissell tube. And a Thissell tube is used to demonstrate osmosis. So what it is this tube that has a solution in it, and we'll just say that it's glucose dissolved in water. And then the tube has a membrane covering over top of it that's similar to a plasma membrane. It's like dialysis tubing. It will allow water to pass, but it won't allow the green solute molecules to pass. So you have a 10% solution inside the Thissell tube. That means 10% solute and 90% water. Then you have a 5% solution in the beaker. So much lower concentration of solute is in the beaker of water than is in the actual Thissell tube. So water is going to move. There's going to be a net movement of water into the higher solute concentration, which is in the tube. So we're going to expect the water level in the tube to rise, and then the concentration of solute to go down in the tube. So that's what happens. That's what happens due to osmosis. So in an animal cell, like a red blood cell, when that cell is placed in what we call an isotonic solution, isotonic means that the solution outside that cell has an equal solute concentration to the cytoplasm inside the cell. So there's going to be some movement of water in and some movement out, but not there's not going to be a net movement in or out. So the size of the cell is not going to change. But if the cell is placed in a hypotonic solution, like distilled water, like a lower solute concentration than what's in the cell, then water is going to move into the cell and cause it to swell and possibly burst or lyse. Okay? If that happens in a red blood cell, it's called hemolysis, H-E-M-O-L-Y-S-I-S, hemolysis. When an animal cell, such as a red blood cell, is placed into a hypertonic solution, that means the solution, the concentration of solute is higher. Hyper means higher. So if it's like a real salty saltwater solution, then water is going to leave the cell, it's going to shrink, and it will die, and we call that crenation. In a plant cell, since a plant cell has a cell wall, it behaves a little differently. In an isotonic solution, it just basically remains normal. The chloroplast and other organelles are kind of distributed throughout the cell normally. If the plant cell is placed into a hypotonic solution that has a lower solute concentration, then it's going to start to swell. It's going to start to fill with water. The central vacuole is going to fill with water, and it's going to push the chloroplast up against the edge, but it's never going to burst because of the cell wall. So we call this turgor pressure. We say that turgor pressure develops. Turgor pressure. And if the plant cell is placed into a hypertonic solution, the plasma membrane will pull away from the cell wall. And you would, under the microscope, you'd see all of the chloroplast kind of cluster together in the center, in one big cluster, because the cell is actually shrinking and the plasma membrane is pulling away from the cell wall. So the cell wall doesn't really change shape, but the plasma membrane pulls away from it. And we call that plasmolysis. So that happens in a hypertonic solution. And then here are the notes. Isotonic means that the concentration of solute inside and outside the cell is equal. And so there's no change in size of the cell. The cell remains the same size. In a hypotonic solution, the solute concentration is lower than on the inside of the cell. And so a plant cell placed in a hypotonic solution will develop turgor pressure, and it will swell, but it will not burst because of the cell wall. In an animal cell, such as a red blood cell, we'll see lysis because the cell will swell and burst. There are little creatures that live in pond water, fresh water, called protozoans, and they have vacuoles. They're called contractile vacuoles that actually pump water out because they are continually taking on water, because that pond water, that freshwater environment is hypotonic. So those contractile vacuoles keep pumping water out so they will not burst. In a hypertonic solution, animal cells will undergo crenation because they are going to shrink because they're placed in a solution with a higher solute concentration than inside the cell. And in plant cells, they will undergo plasmolysis when placed in a hypertonic solution. Now, moving on to facilitated transport, this is just like diffusion, but the substances are, for example, glucose and amino acids. They are polar, or they have a charge. So since they are not lipid soluble, they're water soluble, they need a carrier protein to move them across.